Hi everyone, I'm Karlee Bradley, and I'm a math major here at St. Edward's. Over the past 4 semesters, I've been researching permutations and the patterns contained within them. So, to start diving into what my research is, it's necessary for us to start with a basic understanding of what permutations are. So, in the most basic sense, a permutation is an arrangement or scrambling of consecutive integers starting at 1. The smallest permutation is just the number 1, because it's the only way to arrange that single value. 1, 2, and 2, 1 are the only two permutations of length 2 because they're the only two distinct ways of arranging the integers 1 and 2. There are 6 length 3 permutations, the simplest being 1, 2, 3. And to get the others, we just rearrange the numbers 1, 2, and 3 until we get these 6 distinct forms. Within permutations, we can look at things called blocks, where a block is a set of consecutive positions that also have consecutive values. So in the permutation 1, 2, 3, 1, 2 is a block because 1 and 2 are in consecutive positions within this permutation, and they're also consecutive values because on the number line, 2 comes directly after 1. And 2, 3 is also a block within this permutation. In the permutation 1, 3, 2, 3, 2 is a block, even though 2 comes after 3 in this permutation, but they still form a set of consecutive values. And actually, every permutation, if you consider it as a whole, is a block because all of the positions are consecutive and so are all of the values. And something special about length 3 permutations is that all of them have smaller blocks within them. There are 24 length 4 permutations, but only 22 of them have smaller blocks. And so these two permutations highlighted in blue here, 2, 4, 1, 3 and 3, 1, 4, 2, are special. They do not have smaller blocks, and they're referred to as simple permutations. And so throughout my research, we'll be revisiting simple permutations. Okay, another thing that we can look at within permutations are containment patterns. And so to walk through containment, let's say that we have this permutation, 3, 1, 4, 2, which is one of those length 4 simple permutations. And just for convenience, let's refer to it as pi. What we want to do is find the number of times that the permutation 1, 2 is contained within pi. And to define containment, we say that a permutation pi contains another permutation alpha if and only if there's a subsequence of pi that has the same relative ordering as alpha. So in this case, we want to find subsequences of 3, 1, 4, 2 that have the same relative ordering as 1, 2. And so one subsequence is 1, 2, which obviously has the same ordering as 1, 2 because it is 1, 2. 3, 4 is also a subsequence that has the same ordering as 1, 2 because it's a smaller number followed directly behind by its consecutive larger number. And 1, 4 also has the same pattern, which is a smaller number followed by a larger number, but the numbers don't have to be consecutive. So these are the only 3 subsequences in pi that have the same ordering as 1, 2, meaning that 1, 2 is contained within pi 3 times, where containment is denoted by this little symbol right here. Okay, now let's say that we have this length 9 permutation. Like before, we want to find the number of times that 1, 2 is contained within pi. So we start listing out the subsequences, and eventually we'll see that 1, 2 is contained within pi 14 times. And so for this larger permutation, it takes a lot longer to count all of the subsequences and then pick out the ones that actually have the same ordering as 1, 2, and that takes a long time. So one thing that we want to do is make it more convenient to count containment patterns. So our goal is to write a formula that tells us how many times 1, 2 is contained within another permutation, and we want to be able to generalize that formula for other permutations as well. Okay, and once we find that formula, we can represent it in a generating function like so. And so in this generating function, this x right here represents a set of permutations. This symbol right here is the length of pi, where pi is one of the permutations in the set. C and 1, 2 of pi is what we're looking for. That's the number of times that 1, 2 is contained in pi. and Cn21 of pi is the number of times 2,1 is contained in pi. And to walk through an example of how to use this generating function, let's say that our set of permutations is this set right here. To find f, we look at each of these permutations individually. So for the first permutation, its length is 4, 1, 2 is contained 3 times, and 2, 1 is contained 3 times. For the second permutation, its length is 5, 1, 2 is contained once, and 2, 1 is contained 9 times. And then for the third permutation, its length is 3, 1, 2 is contained twice, and 2, 1 is contained 1 time. So we know how to use this generating function, but we still need to build up to writing this formula for Cn12 of pi. But we're only going to be able to write a formula for Cn12 of pi that only applies to this specific set of permutations, which is the Reed closure of 1, 2, and 2, 1. And so to know what permutations are included in this set, we can inflate permutations. So to walk through what inflations are, we'll go through an example, and we're going to inflate the permutation 2, 1, 3 by the permutations 2, 1, 3, 1, 2, and 4, 1, 2, 3. And so when we inflate, we make bigger permutations. So the first step in inflating this is we look for number 1 in this permutation. We see that it's in the middle position. And we look for its corresponding permutation over here, which is 3, 1, 2, because 3, 1, 2 is also in this middle position. And we can just rewrite that, leaving room for the other parts of the permutation. The next thing we do is we look for 2 and its corresponding permutation, which is 2, 1. But this time we can't just rewrite 2, 1 because we're making a bigger permutation and we can't reuse numbers. So the 2, 1 becomes inflated to become 5, 4, which still has the same relative ordering as 2, 1. Okay, then we look for 3, its corresponding permutation, and inflate that to become 9, 6, 7, 8. And so this is our permutation resulting from the inflation. And notice that it has blocks that have the same relative ordering as each of these permutations. And then the whole permutation has the same relative ordering as this permutation here. Okay. So now that we know what inflations are, we can start building elements in the Reed closure. So initially, we know that 1, 1, 2, and 2, 1 are all elements in the Reed closure of 1, 2, and 2, 1. That's just given. And we're going to generate elements of length 3 by inflating permutations in this set by other permutations in this set. So one example of things that we can inflate is 1, 2 by 1 and 1, 2, because all these permutations are in this set right here. And we continue inflating combinations of these permutations. And eventually, we get all 6 length 3 permutations. So that means that all 6 length 3 permutations are also included within the Reed closure of 1, 2, and 2, 1. To generate elements of length 4, we continue inflating. This time we can use those length 3 permutations in our inflations. And eventually, we get 22 length 4 permutations. But we don't get all 24. And that's because we actually miss the permutations 2, 4, 1, 3 and 3, 1, 4, 2, which if you remember from before, are those 2 permutations of length 4 that are simple. And it makes sense that we can't generate those through inflations because when we inflate permutations, all of our resulting permutations will have blocks within them. And we know from before that simple permutations do not have smaller blocks. So they can't be generated through inflations. That also means that simple permutations are all excluded from our set. That's the Reed closure of 1, 2, and 2, 1, which is important to note. Okay, and so using these observations and a couple other theorems and lemmas that I didn't include in this talk because that's too complicated to go over in this short amount of time, we wrote this formula for Cn12 of pi. So it says that f pi can be represented as an inflation, specifically as an inflation of 1, 2 by alpha 1 and alpha 2. Then we can use this big formula right here to find the number of times that 1, 2 is contained within pi. So to walk through an example of using this formula, let's say that pi is 1, 4, 2, 3. The first thing we want to do is make sure that we can break pi down into an inflation involving 1, 2, which we can, so that's good. That means we can apply this formula. Now we're going to look at each of these permutations individually. So for the first permutation, CN12 of 1 is 0 because 1 is smaller than 1, 2, so it can't contain 1, 2. And for the second permutation, 1, 2 is contained once, which is easy to count because it's only like 3 permutation. But if it were a larger permutation, what we could do is we could break it down into an inflation again, and then apply the formula to the broken down parts, and then just add all of the numbers up. So now we multiply the lengths of those permutations together and get 3, and then we add all of those numbers up, and we see that 1, 2 is contained within 1, 4, 2, 3, exactly 4 times. And so what we can do with this formula is we can actually generalize it to work for any permutation within the reclosure of 1, 2, and 2, 1, with just a few minor adjustments. But one thing we want to minimize is the number of these formulas that we have to write. So if there are ways that we can relate permutations to each other so that we don't have to write formulas for all of the permutations, then that would be really helpful because it would minimize the number of formulas we have to write. And one way we can relate permutations is through different mappings. So to go through the mappings, let's say that pi is the permutation 514326. One mapping we can do is find the reversal of pi, which we get by just writing pi backwards. Simple enough. Another mapping we can do is find the complement of pi, which we get by taking the length of the permutation, which in this case is 6, subtracting off each of the values and adding 1 to them. So for the first element in the complement, we take 6, subtract off 5, because it's the first element in pi, and add 1 to it, and we get 2. Next we take 6, subtract 1, add 1, and get 6, and so on. And so taking the complement actually kind of reverses the relative ordering, meaning that the low numbers become the high numbers become the low numbers. So if you look at pi, we see that in its second position, we have the number 1, and then in the complement, that 1 becomes a 6, and the 6 in pi becomes a 1 in the complement. And the rest of the numbers follow accordingly as well. The last mapping we can do is find the inverse of pi, which we get by looking at the values of pi relative to their positions. So for the first element of the inverse, we look for number 1 in pi, and we see that it's in position 2. And that means that the first element in the inverse is 2. Next, we look for number 2, see that it's in position 5, so that means our second element in the inverse is 5, and so on. And so these are the 3 main mappings that we can do to relate permutations to each other. And so if you noticed, we only wrote the formula for CN12 of pi, and we didn't care about writing one for CN21 of pi, and that's because we can relate 1, 2, and 2, 1 because they're reversals of each other. So these mappings help us eliminate the number of formulas we have to write. And to take it a step further, we can do combinations of mappings. And so when we played around with combinations of mappings called compositions, we found 2 interesting and useful equalities. One of these is that for a permutation pi, if you take its complement and then take the reversal of that, that's the same as first reversing it and then taking its complement. And also, if you take the complement of pi and then take the inverse of that, that's the same as taking the inverse of pi and reversing that. And so these are just 2 more equalities that we can use to relate permutations to each other to minimize the number of containment formulas we have to write. And then also looking at these observations, we found this important theorem that states that simpleness is preserved by any number of the mappings, which means that if I'm a simple permutation and you apply any mapping to me, I will always remain simple in the end. So we know that the simple permutations are excluded from the Reith closure 1, 2, and 2, 1, meaning that we can't use those formulas for simple permutations. And this theorem right here states that we can't transform a non-simple permutation into a simple permutation or a simple permutation into a non-simple permutation, which is important to know. So that means that all simple permutations will always be excluded from the Reith closure. And so after these observations, I wrote a couple of theorems that go a little more into depth of how the mappings relate to inflations, but I didn't include those in this talk because that would take up too much time to go through. But for future research, I like to make generalizations about those theorems and how they relate to equivalent containment formulas. So I want to maybe explicitly state which containment formulas are necessary to write while excluding other ones. And then I'd also like to see if there are other ways of representing permutations to make containment formulas easier to find. So because we can't write simple permutations as inflations, maybe there's another way to write them so that we can include the containment formulas to include them. Here are my references. I'd like to thank the math department and Dr. Mitch for being my advisor the past 2 years, and thanks to the honors program for letting me share my research with y'all, and thank you all for listening.